All right, everybody, let's go ahead and get started. Um, just a few housekeeping points here. If you have any questions, go ahead and type them into the Q&A section. Today should be a pretty short presentation, so we should have plenty of time to answer any questions. My name is Troy Daniels. I am the technical trainer here at SimpliPhi Power. I'm going to be taking you through just a kind of few easy overviews of AC and DC coupling, as well as kind of where our products land and can be used for these various methods. Okay, so a little bit just about SimpliPhi Power, just in case you're not really too up on what we do here. We have a full range of stationary and mobile energy storage solutions. We are a battery manufacturer. We manufacture safe, non-toxic, long-lasting batteries, and we have a wide variety of products. Everything from just the batteries themselves to these all-in-one projects. So basically, when looking at our manufacturing process, we really want to use a lithium iron phosphate chemistry with a cylindrical form factor. So this is kind of what we found to be the most, give us the longest lifespan of a battery, as well as the lithium iron phosphate is the safer of lithium chemistries compared to maybe some of your cobalt-based batteries. Okay, so that's just kind of a brief, for those that don't know what we do, that's really where SimpliPhi, what we do here, and kind of we'll go into more specifics on products as we go through though. Okay, so DC and AC coupling basics. So basically, I'm just going to go through, these are basic definitions. So coupling in context of a PV system, we're just talking about how the solar panels are coupled or connected to a battery relative to its charging. So we can kind of build off of that. When it comes to AC coupling, we're talking about coupling AC power from inverted PV array. So maybe if you've got a string inverter or a micro inverter, that means that you're converting to AC right there, maybe even at the panel if it's a micro inverter. And then we are converting into DC power for the battery charging. Battery, even if you're hearing AC battery, I've heard a few times from some various companies, it's not really an AC battery. This is not accepting AC power. All batteries need to be charged with DC. So if it's an AC battery, it's likely just has an internal inverter that is converting AC to DC. DC coupling, we're just talking about coupling DC power from a PV array. PV is already producing DC. And we're just basically regulating the charge in order to charge a battery bank before it's being inverted to AC power. Okay, so DC coupling. So again, DC power to the batteries. Batteries, that's what they want to see. They're always going to want DC power. And the way we really accomplish getting that PV to the battery is through a charge controller. So basically, we have this charge controller, and what it does is it actually takes the PV power and can actually control DC power voltage and amperage. So we have specific set points that we would supply as the battery manufacturer, and the charge controller can make sure that those are being hit. There's definitely some PV arrangement considerations when it comes to this, compared to maybe a grid-tied system. Most of the time, you're going to have smaller strings. Even if you're using a fairly large, let's say maybe a 600-volt charge controller, you likely are going to have fairly smaller strings compared to what you're used to using a grid-tied inverter. You're still supplying AC from the inverter. So again, we're kind of a direct path there. We're going PV, charge controller, battery. So we're charging at a direct path, but we're still inverting to AC from the inverter. So again, what do charge controllers do exactly? We're talking about regulating DC voltage and current going to the battery bank to hit a specific set point and battery limitations for charging from a DC source. So whether that's the max amps that can be allowed to go into that battery, the exact voltage, you're talking maybe 3-stage charging, bulk absorb and float. These are all programmable with the charge controller. This is DC coupled charging. Sources for DC, can be, doesn't just need to be PV. It could be things like wind and hydro are often set up to charge controllers as well for DC. And you might hear, PWM versus MPPT. MPPT is really kind of where I would prefer to use these typically on lithium batteries. That's maximum power point tracking. We could do a whole presentation on the difference between PWM and MPPT, but really for lithium purposes, it's typically best to go with the MPPT charge controller. So here's kind of an idea. I should probably update this, but where this is a bit confusing is really the PV is going into the charge controller and the solar is being charged here before it's being inverted. So this line should really go to the batteries. It is still blue, and this should match up too, but really we're saying DC, DC, and then this is where we're inverting to AC through the multi-mode inverter. And just quick kind of little bit about DC coupling. I think oftentimes it gets a stigma that it's only grid tied, or off grid, but really, grid tied systems, DC coupled, hybrid systems are really efficient as far as battery charging goes and still hold most of the same functionality. Okay, so now we're going to AC coupling. So here's what we're talking about with AC coupling. We're talking about AC power coming off the roof. So, or maybe even off the string inverter. Let's say if it's on the ground. But basically we're saying that solar is being inverted already, and we need to get it back to DC to charge the battery now. So this could be micro string inverters. And really what we're doing is we're actually using the internal charger of the battery base inverter. So if you're buying a multi-mode inverter, you'll often see it says inverter charger. That charger portion cannot be used DC coupled, but that is an AC charger, basically saying you can take AC in and we can convert it with that charger. So we can charge the battery with the internal charger of the battery base inverter. PV arrangement considerations here are actually less. We're talking, this is what typically why installers like grid tied arrays. They're easy to install, bigger strings, and if it's an existing array, it's already in place. And we're still supplying AC from the inverter. So again, we're using that inverter's built-in charger to charge the battery. It's very similar to charge control. Still we're setting the set points, things like that, max charge, voltages, and really the big difference here is we're taking AC power and supplying it to the battery as DC, instead of the charge controller that just takes DC and regulates it to remain as DC power. But the source must be AC in this situation, whether that's a grid source, if it's AC coupled, as we're talking about PV, that specifically needs to be an AC outputted source. It can even be things like generators, technically can go through this charger. So basically, when we're looking at AC coupling, we're looking at frequency shifting, which is, I would say, really the main mechanism I see as far as what's been used by battery-based inverters. And frequency shifting is just a mechanism used in battery-based inverters to regulate or control a grid-tied PV inverter's output and really just functionality. When your grid-tied array goes down, first and foremost, we have to basically act as the grid now to make sure that they are able to come back online. And once they are online, these grid-tied inverters, they require some regulation. So we actually need to use frequency shifting to ramp up and down the output of the solar array. Now, I just kind of like, a lot of stuff I've been finding lately that I just want to go through and mention is it's actually very, very crucial that you look at what the grid-tied inverter is, what its frequency range is, and understand really what the frequency profile of that micro or string inverter is to understand if it'll actually work with the battery-based inverter. I see a lot of older microinverters that are not ready to just be hooked up to a battery-based inverter. They actually require maybe upgrading. I think we just had a system basically required an upgrade of the Envoy for an N-phase system. So it was an older system and it requires the newer Envoy in order to accept a frequency profile. If the range is too small, it's oftentimes that this frequency shifting will not work perfectly and you will not end up with a very smooth battery charging when it comes to this. So definitely I would say call the battery-based inverter manufacturer, and I would also call really the grid-tied manufacturer, and just they typically understand what these battery-based inverters do and can kind of lean you in the right direction as far as what their frequency profile is and if it'll work or what steps might need to be taken to ensure that it works. So this is a very crucial part of this that I think a lot of people think it's just as easy as plugging in and forgetting about it, but really, if it's an older system that you're adding a battery to, it can take some nuance. Okay, blackout relays is a thing you might hear. Blackout relays still used sometimes, but this is basically just a different way of AC coupling, where we're going off and on. Basically, it's a little bit easier. And again, grid-tied inverter considerations. Really got to think about that. I mean, honestly, SA compliant inverters, you're probably okay, but anything else, I would check on the frequency range and talk to the grid-tied manufacturer. Okay, so this is a kind of diagram here. We can see the PV array being inverted here on the right, and from there it is actually going typically to the critical loads panel and then into the inverter's charger to be charged. So the batteries can be charged and inverted. If the grid goes down, most of these battery-based inverters, I would say actually all of them, have built-in transfer switches for the most part if they're grid interactive, and can disconnect from the grid and invert your batteries just to that sub panel. Okay. So we're going to talk a little bit about the access, and I just kind of wanted to go through. So the access is our all-in-one unit. We have two different access units, one with Schneider and one with Solarc. These are just the internal inverter and charger components. And we actually have 4 different models of access. So we have the Schneider access that has 3 batteries, the Schneider access with 4 batteries, the Solarc access with 8 kW, sorry, it's a little mixed up there. Some are batteries and some are kW. And the Solarc access, 12 kW, which actually has 6 batteries. So basically, the thing we need to watch out for is what's the maximum PV per the warranty that we can add to that AC when we're AC coupling. If we're DC coupling, we don't really need to worry about max PV. The charge controller can typically regulate a pretty hefty amount of PV without any issues. The only thing that might blow in that case is the charge controller. We really don't want to rely on AC coupling is not super fluid yet, so oftentimes you might see more power go into the battery than expected. So the limits are 5.7 kW for that 3 battery Schneider. For the standard 4 battery Schneider, 6.8 kW is the max PV allowable to AC couple. The Solarc 8 kW model, 7, and the 12 kW model, the largest, 7.6, is the maximum allowed AC coupled PV. Okay, I think that slide was a little bit out of place, but that's okay. Well, I think we're going to let's go through applications real quick, and then I think I've got just a little bit at the end there regarding the access solution. Okay. As far as DC coupling applications off-grid, again, this is really where it lies. Everyone kind of thinks off-grid when they think DC coupled. And you can actually even use a float charge in this kind of scenario. Typically, we don't recommend float for AC coupled or grid tied, but when it comes to DC coupled or definitely off-grid, we can actually utilize that float charge. Battery backup, again, we still can use DC coupled just fine in these situations where they're, we're talking hybrid system here, grid tied, but DC coupled. Still can go into island mode. The charging is going to be a lot more seamless, and you won't have to worry about as much considerations on the sizing and worrying too much about the AC coupled array. And you can still use these features like cell, time of use, peak load shaving, and all of those. Actually, time of use tends to only be available in DC coupled for most of these battery-based inverters. Large scale C&I, definitely, we're talking DC to DC converters, large scale stuff. It's definitely, I see it. DC to DC, definitely I see a lot. Medium scale built-in MPPT charge controllers, these are pretty handy too. We're talking large scale charge controllers that can charge a pretty large battery bank. As far as PV considerations, if you're building out a huge array and it is a C&I project, DC coupled, you might see some efficiency stuff where you need to add optimizers or something along those lines. And it can be a little bit more cumbersome as far as the installation goes. AC coupling, I think we all kind of think battery backup. This is probably the biggest thing we think about when we think about AC coupling. We're talking retrofit. So, existing array already in place and actually adding a battery to that system. In a grid down situation with AC coupled systems, we can actually bring back online that PV array. We can charge efficiently and we can discharge the battery to the critical loads. Large scale C&I, AC coupling definitely is really helpful when it comes to large scale C&I as it makes ease of PV installation it's definitely a lot easier than we're talking DC coupled here when it comes to stringing PV in a large scale. There's a little bit of efficiency loss. You got to think you're going DC to AC, back to DC, back to AC. So it's a lot of conversions there. And you can even add batteries to existing large-scale PV systems. As far as the large-scale stuff goes, frequency shifting when it comes to, let's say a 100 or a megawatt-hour inverter or megawatt inverter is fairly more efficient, I would say, than it comes to these residential dynamics when frequency shifting. So when we're kind of doing, applications, we often think, I think there's kind of two realms here, retrofit versus new system. And really, what are the considerations here? So existing PV and AC coupling, it makes sense if the PV is already on the roof, as basically if we tried to DC couple a system to add a battery that's already in place, we're going to be doing a lot of rework. We're going to be pulling up panels, pulling out wires. So if the system's already in place, definitely makes a lot more sense just to go AC coupled. The island mode and the grid tied inverters still come back online when we have a power outage. Again, I think there is a misconception of DC coupled grid tied systems. They work completely fine. I think that's derived a lot from the retrofit challenges that I just mentioned. But again, if you're starting from scratch, it definitely oftentimes makes sense just to go with DC coupled. If you have a customer that knows they want a grid-tied battery-based system and they have no grid-tied PV already, go DC coupled. You'll save yourself a lot of headache. And again, I talked a little bit about efficiency, but let's talk efficiency of AC versus DC coupled as far as shading goes. Obviously, when you have grid-tied inverters, you often have optimizers or these microinverters themselves. So, you know, there's definitely a level of higher efficiency there as far as PV production right out of the gate. DC coupled does have the option for certain things like optimizers. So it is not that we can't do that. It's just that it's not as standard. All right, rapid shutdown. DC coupled versus AC coupled. I write local jurisdiction in all of these. If I ever mention the word rapid shutdown, I write local jurisdiction, or really anything with the NEC code. It changes everywhere you go, so don't be telling them SimpliPhi said this and then it's different. It is going to be different everywhere. So every inspector is going to have a little bit of a different understanding of what they interpret. If we are talking about DC coupled, though, we might just be talking about a few different things. You know, if it's off-grid, oftentimes I've found even with rapid shutdown compliant systems, they just need a shut-off box coming in when it goes into the house from the ground mount. Modular level shutdown. If we are going DC coupled, we probably need some DC optimizers or an RS-only PV attachment. This could be something like the Tygo. I think Midnight makes one too. And these are just, they clip to the panels just to add that level of rapid shutdown compliance. So that can be super helpful if you're a grid-tied hybrid system, DC coupled, you might need to add these rapid shutdown attachments. They're pretty inexpensive too. Okay, AC coupled, you're probably already good. If you have microinverters, or even a string inverter that was set up to be modular level shutdown with DC optimizers, you probably don't need to worry too much. Your RS compliance is already there. Adding a battery in line does not necessarily change the RS compliance. So if you had microinverters on the roof that were modular level shutdown for rapid shutdown compliance, adding a battery-based system in line with that is not going to affect your compliance there. Okay. A little bit more regarding system design. I think I've talked a little bit about this, but limiting amps through the charge controller is very easy to do. You know, the charge controllers are very efficient at doing this, and you're just not going to have as many issues. If you set the limits right, even if your PV is pretty large or if the output is going pretty high, it's pretty straightforward. Smaller strings, though, as I mentioned, and typically you need to use a combiner box. Wiring runs, you know, we might be doing smaller runs and then running a larger run. But grid-tied limiting, you know, it's a lot easier in this case. The charging is a little more seamless, and the critical loads panel, we're still supplying power there. When we're AC coupled, limiting the amps to the inverter's internal charger it can be done. And basically, there's a limit that can be set, but we kind of need to understand that there's still kind of a gray area there when it comes to functionality of frequency shifting, and if that limit set on the inverter will actually hold true. From what I see, oftentimes, if it's maybe an older microinverter and the frequency is not perfect, it will not hold true. So that's where we have those limitations that I showed you earlier. If you're AC coupling, as far as PV goes, you still can sell excess to the grid. And really the benefit, again, is the larger strings and less wiring. Considerations on the CNI. I talked a little bit about this. We're talking, I won't bore you too much on this slide. Really just kind of the thing to understand is when it comes to system design considerations, CNI for AC versus DC coupled, I would really say it comes down to how you want to string up your PV. If you've got a large, megawatt, let's say 5 megawatt array, that's a lot of work with even a large team. So it might make sense to go AC coupled oftentimes. And if it's a microgrid, just know that, so typically we would never recommend going AC coupled off grid on a residential scale. But the good news is when you're AC coupling on a CNI scale, a large scale, typically those larger inverters that are designed for those large battery-based inverters actually basically can act as your grid. And they're very efficient at doing that. Okay, so our products, we have our standard battery, 2.9 and 3.8. These are our biggest sellers. They don't care their ability for DC or AC coupled. They just want to see DC power. So as long as they're being charged by DC, they could care less which one they really are. You'll still need a battery-based inverter no matter what. And again, we got to think, AC to DC to AC and DC to AC with a DC coupling. So, with AC coupling, we have one extra conversion there versus DC coupling. I would say this is not even typically 48 volt is almost always recommended for AC coupling. I can't think of very many battery-based inverters that do 24 volts and AC coupling. So pretty much we'll always be recommending a 48 volt battery when AC coupling. We've got our access solution. These come in both AC and DC coupled. So I mentioned earlier the Schneider and the Solarc. And again, these can be AC or DC coupled. There's MPPT option for the DC coupling when it comes to the Schneider unit. The Solarc actually has it built in already. These are both higher voltage charge controllers, meaning that we're trying to take the ease out of the PV considerations here and allow for larger scale, larger strings when it comes to stringing up the PV to these DC coupled systems. They're both ready for AC coupled. If you don't go with the charge controller option, you can still AC couple with the built-in charger. Again, with those grid-tied compatibilities, run projects through us. If you're gonna AC couple, I would run it through us. Say this is the model of grid-tied inverter I'm working with now. We can help get you in touch with the right people to make sure that it works, or if we need to update certain settings like the step rate or even get a frequency profile added to the microinverters. Be sure to specify when you're ordering the AC versus DC coupled access. The Solarc, it doesn't matter. It comes with both. The Schneider, you just need to specify which one it is with your distributor. Okay, all these access solutions have an automatic transfer switch built in. This is built into the battery-based inverter. So just know when the grid goes down, this automatically will switch over to critical loads and isolate from the grid. They're also NEMA 3R, so they're outdoor rated already, which is really helpful when it comes to AC coupled systems. Most of your equipment, if not all of your equipment, is already located outside, and we don't have to ask to go into the home at this point. We can add this to an outdoor installation just fine. Okay, here's the slide. Looks like it made it twice in the presentation. Again, these are the limits for AC coupling with our access solution. So it's in the manual, section 3.1.1, but just know that these are the limits. And these limits are kind of designed by both us, the inverter manufacturer, and even some code standards. So we kind of take the lowest common denominator of those three. Okay, if you're looking for tools and help, things like that, just FYI, call our tech support line and really our pre-sales line. If you are just working on the project, hit pre-sales and one of our SAs will be able to help you out. If you have some support issues, give us a call on the support line. We're happy to walk through installation, set up things like that. And if you need any tools or design tools, you can go to our website. We've got tons of cool ones up, like the battery sizing tool, some engineering services, and even lead acid replacement guides, as well as I believe the wiring guide is up now as well. Actually, we even have a LCOE calculator for looking at ROI as well. Okay, short presentation, but I'm going to go ahead and pop into the Q&A here and see what questions have come through. If you have a question that I didn't get around to, go ahead and type it in right now. can you split the support from a PV array to handle AC loads during the day, like air conditioning, but still charge the battery for nighttime? How does this work? Yeah, I mean, it's gonna, you know, the PV is gonna, you can set the max PV there, and then really it's gonna be, you know, whatever, if the loads are present and it's on that critical loads panel, then it's gonna take priority over charging. So it really is more of an automatic solution. Are there greater transmission losses in AC or DC coupled? So I would say AC coupled, definitely more loss there. What are blackout relays? I'm not sure exactly the full, I'm probably not the expert to talk about that, but basically just a relay that, you know, turns off and on that ability for the microinverters to turn off and on. How do you integrate a generator into an AC coupled solution? You probably, you know, it's kind of tricky, to be honest. Oftentimes it requires an external relay. So you got to be kind of careful when applying a generator to an AC coupled situation, and just follow the guides of the inverter. So if it's Schneider, if it's Solarc, just check out the guide and make sure you have all the parts and pieces you might need to prevent backfeeding. How do you determine whether you can use an existing grid-tied inverter with a battery backup? I would check on the frequency profile and then compare it to the frequency profile of the frequency shifting of the battery-based inverter. That can be found in the manual for each inverter. But really, I would just say call is more. You know, if you call Enphase and you say, hey, I've got some M250s, with this Envoy, they're going to tell you what is needed with that battery-based inverter. What are optimizers? Optimizers are basically just parts that go onto the PV array to ensure that, you know, let's say you have shading on one panel and not shading on another, that whole string doesn't go down. Now we can optimize the power on the remaining panels. Okay, looks like that was all the questions. I will be posting this online, the recording, if you want to rewatch it, as well as sending out some slides. So I appreciate everyone's time, and feel free to email me if you have any questions beyond this. Thank you.